All right, so today we will start the second phase of our lecture. We are going to talk about some of the parallel computing methods and using some application as a demonstration for using those parallel algorithm or parallel computing methods. Okay, and also we will introduce the application you're going to implement it for your homework 2 and 3 in this chapter as well. Before we moving on to GPU programming. All right, so as you can see, we will introduce 4 very basic and commonly seen parallel programming strategy or methods, including embarrassing parallel computation, divide and conquer, pipeline, and synchronous computations. And some of those computation, you probably already seen it in other area like CPU design or your algorithm course. So you can see parallel computing techniques basically are everywhere, right? And some of them you probably have used it or known before. But of course here, those are the computation we use to parallelize our computation and parallelize our algorithms. And at the end, we introduce a load balancing, which is very critical to parallel program, because again, the computing time or the performance of a parallel application is depends on the last finished task of the parallel program. So we usually want to make sure the load is balanced, right? So everyone can finish roughly at the same time to avoid some idle or resource wasting from the parallel computation process. Okay. All right. So we will spend a couple of lectures talking through all those computations and the technique for load balancing. Okay, and for each of the parallel computations method, we will use a couple of applications as example to show you how those computation can be applied to solve a parallel computing problem. Okay, so for embarrassing parallel computation, we will talk about image transformations, Monte Carlo method, and the Mandelbrot set, where the Mandelbrot set will be your homework 2, as you probably already find out from our announcement for the homework 2 spec. Right? So first of all, the definition of an embarrassing parallel computation. So what is an embarrassing parallel computation? It's actually the simplest and the most ideal form of a parallel computation. It means the computation can be divided into a number of completely independent tasks. So that means you don't even require any communication or synchronization among those tasks during your parallel computation. So it's an ideal case, right? Because it doesn't suffer from any of the overhead we mentioned from parallel computation. Of course, this is an ideal case, and this is one of the parallel computing method we would like to see. And so as you can see, the communication or the synchronization will only happen at the beginning of the computation when you probably try to scatter the input data, right? Or initialize the state, or happen at the end of the parallel computation to try to collect the results or aggregate the results. But during, within the computation, parallel computation, there's no communication or synchronization. So they are completely independent tasks. Okay. Also, it's an ideal case, but of course, this is also probably the most commonly seen case for parallel computation. Because if your computation is a embarrassing parallel computation, or could be an embarrassing parallel computation, that probably imply you can achieve great scale up, right, and very efficient parallel computations. So of course, people try to, right, or hope their computation is a parallel, embarrassing parallel computations. And as we will introduce some distributed computing framework like MapReduce or Spark, also they basically follow this model. Right? They try to they actually focus on or specialize on those embarrassing parallel computation tasks. Okay, so as we mentioned, this is actually a common case for many parallel computation applications. And one of the example is image transformation. Okay, so image transformation are the computing tasks that try to do some image processing or try to apply some transformation operations on image, and they are very commonly seen as a low-level image operations. So, for example, like shift, right? If we want to shift some object on our screen, right, to the right side, the left side, or some other position, as you probably know, what happened is we will basically try to move the pixel, right, to another location by adding a shift distance to your axis or y or your dimensions, right? Like most of the image, we know they are consist of pixels. So those operations can be applied on those pixel independently, right? By operate on their coordinates. Okay. Basically, what happened is you would like to perform the operation or the computation showing over here, right, on each of the coordinates of individual pixel. So each pixel can be applied this operation independently. So this is what we call the embarrassing parallel computation. Okay. Okay. So similarly, right, many image transformation operation fit this model, right? Like scaling is also similar. What happens is we will try to multiply a scale factor to the coordinates, right? And so again, this operation can be applied for individual pixel independently. And finally, the rotation is the same, right? Also, the operation might seem a bit more complicated, right? Like showing over here, x plane will equal to x multiplied by cosine theta, then plus y sine theta. Okay, theta is the angle we try to rotate. Okay, so although the computation involve x, y, or even z in the three-dimensional case, but remember, all those coordinates are independent and individual to each pixel. So those operations still only apply on each pixel independently. So the computing task for each pixel is an independent task. Okay? So that's why image transformation actually has a very high degree of parallelism, right? Especially if you have huge high resolution, you have millions of pixels, then that means they can all be processed individually. So that's why, as you can see, a GPU was specifically designed for image processing, right? Because all those image processing operations are highly highly scalable and parallelizable. So GPU can fully utilize for those operations. Okay, and so obviously that's the one of the commonly seen case, and that's why we even have a GPU device for this kind of computation as well. Okay? And the related thing you should know is that even in embarrassing computation individual task cases, one of the things you should you should pay attention is how you partition the tasks, right? Like image, you can actually partition it in different many ways, right? um, Partition the image to 1 pixel per task is one of the basic form, right? But that will probably produce too many tasks. So as we mentioned, like in OpenMP, for task scheduling, if you have too many tasks, usually there could be some overhead as well. So sometimes you don't want to uh, you don't want to partition the task to be too small, right? And also another thing related to partition is it might affect the communication or the management effort during your payroll processing. Okay? Um, for example, over here, you can see this image. We can partition it in square, in row, or in column. Okay? And sometimes the computation workload or the computation time for each partition still may be different, right? Because like the application you will see in homework 2, each pixel may process may demand different amount of computation workload. So in that case, how you partition will affect the load balancing results. Okay. Also, in some case, after you do the partition, maybe you need to exchange some information before you can do the computation on those tasks or partition. Okay. So so the amount of information you need to exchange maybe depending on the length of your boundary, right? Or like in this case, you can see all those 3 partitions may resolve different lengths of the boundary between the partitions. So it might affect how much communication cost, right? You may need to consider. Okay. All right. So even for embarrassing computation, partitions matters because it may affect the computation or communication workload in your process during the computation. Okay. So let's see example. Okay. Usually we will not schedule 1 pixel as an individual task, right? So in this case, this example that we try to partition the computation by row. Okay, and since you have complete the homework 1 using MPI, you can see the pseudocode we have here is a payroll program, right? And follow the MPI programming model. So we have a master and the slave. Okay, and the master is doing the work to do the task partition and scheduling, while the slave process will simply receive tasks from the master and start doing whatever the image transformation operations on that pixel. Okay, and in this case, you can see because the task is partitioned by row, right? So here we will simply go through. We will try to each task. We will you can see every task we will only give the index of the first row of each task, so that each slave, when he receives the row number, he will just know that the following 9 rows will also need to be processed in this single task. Okay, that's basically how we do the partition over here. Okay, and in this case, of course, this is not the optimized code. It's just example. So you can see over here, although he received the task by 10 rows at the time, but when he returned the results to the master, it returns it individually for those pixels. That means the master, right? It has to try to receive those pixel points one by one. And for all the parallel program, another important thing you need to take care is how to determine the termination, right? When do you know the computation should end? So over here, you can see the master simply try to count how many pixels it receives. And when he receives all the pixels, right, all the results, then he knows he already processed the whole image. Okay. And of course, because we have to when you collect the result and you can use dispatch those tests, they could be processed in parallel. So that's why we have a temp map as a buffer, right, to temporarily store the new results so that we will not override the old values in the image, which will actually need it for the slave, right, when he try to compute the new value. Okay. All right. So this is a classic, right, the basic implementation for how we could process an image in parallel, right, by dispatching those tasks independently to those slaves. Okay. But however, you will see that the load of this implementation on each worker or slave process will only be equal if the processing time needed for each pixel is the same. Because when we try to dispatch the computing task, it is like right, it's a static scheduling strategy, right? So we only ensure that each slave process try to process the same amount of rows over here. Um, but in your homework too, you will find out this is not the case for the image you're going to generate or going to process. So in that case, you actually need to design and implement a dynamic scheduling strategy to ensure the computation time is balanced across all the slaves. Okay. All right. Okay, so as you can see, for image transformation is really simple and they have lots of it's very fit for parallel processing. Okay, so that's why GPU is designed for image processing. Okay, the second example is more general, is a general computation, and it could be applied on a wide range of applications because it is a class of algorithm called the Monte Carlo method. Okay, the definition or the concept of Monte Carlo method is referring to a class of computation algorithms that try to solve their computation problem based on repeatedly random sampling techniques. So this might be your first time heard about Monte Carlo method, but if you heard about deep learning, right, the gradient descent algorithm, then it's also a form of Monte Carlo method. Because you will know when you try to solve the problem, you also try to depends on the result of repeating random sample computation. Okay, so this actually be widely used for solving many complicated optimization problems. Okay? And this method is actually first proposed by the famous uh, John von Neumann, okay, back in 1940, and it was again designed to solve some complicated science computation equation. And unfortunately, it was tried to design the nuclear weapon. And there are some very complicated equation need to solve when they try to develop a nuclear weapon. And so John von Neumann come up with this method. So it can be able to solve those equations and reach its goal. Okay. So as a result, it has become a very common method to solve many other complicated equations, especially for those scientific simulator. Okay, because as you might as you could imagine, right, for those fundamental material science or physical science or aerodynamics, all those area, they have all kinds of equations, right, to try to capture what happened in the science domain. However, those equations are so complicated that sometimes it's very difficult to find the optimum setting, right, in order to solve that equation. So what you could do in a simple way is try to guess, right? So you will just try to, you can guess different solution and use the equation to evaluate the result and see which guess or which sample is the better, can give you a better results. And so you can keep repeating doing this in order to find out how you could adjust your guess, right? And eventually you are able to reach that optimum results. So as you can see, this is exactly what happened on the gradient descent algorithm as well, right? For deep learning. Okay. So this method actually can be applied in many domains. Okay. And as you can imagine, the reason we mentioned this method here, because this method, in order to apply this method, is actually a form of embarrassing parallel computation, right? Why is that? You probably have implemented this in your lab one, right? When we ask you to use MPI to solve the calculation of pi, okay? So that's a classic Monte Carlo method. And the way we know, as we all know, although we know the definition of a pi, actually pi itself, the value of pi itself is a very complicated number, right? So that means if you want to know the exact value of pi, it's not as simple as you might think. Okay, so one way to do that is using the Monte Carlo method, and the idea is that as we all know, although we don't know the value of pi, but we know that, right, the diameter of a circle, right, like over here, if a unit circle, then the diameter, right, the length is 2 by 2. We can use a 2 by 2 square to fit that circle, right? And if imagine right now we just randomly try to generate some coordinate in this area, right? We know the possibility. We don't know the value of pi, but we do know that the possibility of that sample coordinates falls into pi or falls into this circle is pi over 4, right? Because that's the area of a circle divided by the area of the square. So we know that possibility. We know that probability. Okay. So what we could do is simply try to repeatedly generate some random sampling coordinates. And we can follow by the definition to check whether the coordinates falls into the circle, right? Because if it falls into the circle, that means the distance from the coordinates to the center needs to be smaller than 1, right? If it's smaller than 1, by definition, we know it's within the circle. And if it's larger than 1, by definition, we know it's outside the circle. So by simply generate a bunch of coordinates point, then we can know we can calculate, right, based on the result of those sampling results, we can calculate the probability. Okay, so for example, if we have 10,000 sampling points and the the result shows that 7,000 or close to 8,000 points are within the circle, then we can use this information to derive what's the value should be for pi. Okay, so you can see we know nothing about this equation, but we can just, based on the sampling result, we can derive the value of pi. Okay, so this is a classic Monte Carlo method. Okay, and the property of Monte Carlo method, there are very good, many good property of Monte Carlo method. That's why it has been used to solve those complicated equation, right? First of all, it can be solved by just sampling, right? So you don't know the detail, but you can always do the sampling and then derive the result. So it can be easily applied to solve many complicated equation. That's his first advantage. The second advantage is that you can see the accuracy or the precision of the result. It depends on the number of samples, right? So for most of the Monte Carlo method, if the result will be more precise when you generate more sampling points. So that means you can trade precision for or you can trade computation for precision, right? So if you have abundant computing power, then you can just keep sampling and keep improving your results. So and also the computation, right, is purely embarrassing computation, because the result of each sampling point is considered and can be calculated independently. So this computation is embarrassing parallel computation. So that's why people try to build supercomputers. That's why people are very interested in parallel computation, because parallel computation can solve embarrassing parallel computation application in efficient way, and this method can be applied to solve many complicated problems. So that's why we have those powerful parallel computation machine to do the job. Okay. All right. So we, of course, that's the simplest example. So that show you one more example that's a bit more complicated, but basic follow the same concept. Okay, so the second example for Monte Carlo method is to compute the integral, right? You must know that sometimes it's hard to compute the integral, or you don't simply want to remember the equation, right, to compute that. So an easy way and a best way for computers is actually again to apply the Monte Carlo method. So you can even solve the integral problem on arbitrary functions. Okay, and the idea is the same as before, right? Because we know by definition, integral means the area, right, beneath this line, right, described by your function. Okay, so again, that means if we can, right, again, have a square, right, or rectangular, right, to cover the whole area of your function, then by randomly generate some sampling point, we can again use f of x to evaluate or to determine whether that coordinate, that sampling point, is above the line or under the line, right? If it's under the line, that means it's in the area of your integral results, right? So again, just by sampling points and by evaluate each of those coordinate according to your given function, then you can similarly derive the area of this integral by the integral value of this function, right? Okay, so so basically we don't need to remember any equation and any arbitrary function. We can always use this strategy to compute the results. Okay. But however, this computation is not very efficient, as you probably could imagine, because the efficiency of this result will depending on the area, right? How much area is covered in this, in this rectangular, right? If this rectangular is huge, right? If this x max is a huge number, then we actually need the number of sampling point units should be proportional increase, right, to this area. So if this area is larger, that means you need more sampling points in order to get a more precise results. So the efficiency will depending on your equation, and sometimes it may not be very efficient to compute the result using this method. Okay. So of course, there are other more efficient Monte Carlo method exists in order to compute the integral value. But of course, it's not the point of this course, so we will not introduce those methods. Okay, all right. And the third example, okay, is Mandelbrot set. So this is your homework too. Okay, so let's see what is a Mandelbrot set. Okay, so the Mandelbrot set is a set of numbers, okay, and a set of complex number. So hopefully you can still record a complex number means a number that consists of the real number and the imagined number. Okay, and we can usually indicate those complex number on on this coordinates, right, on this imagined and the real number coordinates. Okay, so any complex number can be represented as a point, right, as a coordinate in this area. Okay, all right. And the Monte Carlo and the Mandelbrot set, right, is a set of numbers that satisfy the rules below. Okay, and this row is described by a repeated iterative computation equation. Okay, and what it does is as shown over here, right? Z is the value after your iterated computation, and C is the complex number. We try to determine whether it's within the Mandelbrot set or outside the Mandelbrot set. Okay, and the way to identify it is we repeatedly compute it by this equation, right? So you can imagine as showing over here, right? This is the iteration in our computation, and y-axis is the absolute value of a complex number, which means the distance, okay, to the 0 point. Okay, so as you can imagine, as your iteration goes on, the result of your z, right? If k iteration means the value of zk. Okay, so any given complex number, it will transform from z0 to zk, right? And the value will just keep changing. So the distance to the origin will also keep changing. Okay. So this is what we need to evaluate for each complex number. Okay. And the interesting point for Mandelbrot set is that what happened is, I don't know why, and it probably could be proved, but in any way, the result is that if the distance of zk over 2, okay, if it's at some point it's over 2, then he will just diverge. Okay, he will just keep going up. He will never comes back. On the other hand, some of the value, no matter how many iterations you compute, his distance to origin will always within 2. Okay, so for the value, okay, for the complex number that will always within 2 are the complex number within or belong to the Mandelbrot set. Okay, so we use this iterative computation to evaluate whether a complex number is within the Mandelbrot set or outside the Mandelbrot set. Okay, and theoretically, you actually have to check it, right, for infinite number of iterations. But of course, no, we don't have infinite number. We don't have infinite computation power. So in your homework too, or in reality, usually we have a max iteration. Okay? If you can, if your distance can within two, right, until you reach the maximum iteration, then we determine this complex number as a member of the mandible set. Okay, right? So this is the definition of a mandible set. Okay, it's a result from some mathematical equations. Okay, all right. So you might wonder. Hopefully now you understand the definition. Then you might wonder why it's matter, right? Although it's magical, it's interesting, but how it matters, right? So what matters is because a mandible set is is a form of what we call the fractal. Okay, what is a fractal? Okay, fractal is a behavior. Okay, we observe from the natural world that something just showing a self similarity in various scale or in various degree. Okay, what that means is, as we can show over here. So the plot over here is what you need to show to compute from your homework too as well. Because as you can see, this area is what we explain, right? This is represent a set of complex number, okay? And the number, the complex number that's in black color are the are the complex number belongs to the mandible set. Okay, while the white color, right, means the complex number outside the mandible set. So the result of a mandible set is this pattern you see over here. Okay, and this pattern actually is right is an example of fractal. Okay, why is that? You can see the picture below. Okay, those beautiful pictures are what we taken from this one in different scale. When we try to just keep zoom in on the image or on some area in this pattern. Okay, and what happened you can see is you can see over here, right? This pattern looks exactly like this one, but this pattern is actually not this one. This is actually just the pattern we see right over here, this tip. Okay, so this small pattern, actually, if you zoom in, you will find out that small pattern looks exactly the same as this large pattern. So we can observe the self similarity, right, in different scale. Okay, and what repeated is not just this pattern. If you look at other picture, you will also find out there are also other patterns exist, just repeating in this whole pattern, somewhere in this whole pattern in certain scale. Okay, this is an interesting result, but this is what happened in the natural world, like crystal or some other material science or something. Somehow, we just could observe those kind of pattern. And when we try to model it, right, or we try to represent it, and then we need to derive some mathematical equation and try to capture or show that pattern. Okay, so mandible set is one of these examples. Somehow, this is the equation. This is example that we can find an equation, a mathematical equation, to describe a pattern with a fractal. Okay. Okay. So this is even more beautiful pictures, right? But this is still the same as we showed before. But this one, you can see more colors in this picture because the color of the pixel or the coordinates is depending on the iteration you find it is outside the mandible set, right? Because as you can imagine, some of the pixel you can identify it's not belongs to the mandible set in the probably even the first iteration, right? And some of the pixel you will find out it outside its distance will goes over 2 in a later iterations. Okay, so the color over here shows that if you find out you are not a mandible set in a later iteration, then your color will become darker. Okay, so of course the black one, right, is always within the distance of 2. It's a mandible set, so its color is the darkest, so that's black. Okay, but if some complex number, some coordinates, you can immediately find out it's not mandible set, then its color will be lighter. Okay, so this is how we get this result. And you can see those fractal, right, appear even more in this image. Okay, okay. All right, so that's the story of mandible set. But for this course, what we only care is computation, right? How we parallelized computation for solving a mandible set problem. Okay? The computation is actually not that complicated because, of course, this is an embarrassing parallel computation. So we only need to consider the computation on each individual complex number at a time, right? And in order to implement this computation, of course, we first define a data struct to represent the value of a complex number, right? Because we have the real number and the image number of a complex number. So we use a data struct to represent it. And just try to refresh your memory. This is how we can do the multiplication and addition on complex numbers. Okay. So anyway, we don't care about this too much. As you can imagine, if we have this data struct, we can follow this definition to do the computation. So we can do the complete computation for each iteration, right? Okay. So here is what we think from the previous page. All those statements doesn't really matter. The result is we can know the zk value from some iteration, right? And of course, in order to make sure the distance is larger than, whether it's larger or smaller than 2, sometimes we don't bother to take the square root, right? So we simply check the result, whether it's larger or smaller than 4 instead. So make it simple. Okay. And you can see this is just a while loop, right? Keep repeating to check whether the distance to origin can be smaller than 2. Okay. And if it's larger than 4, right? Before you take the square root, if it's larger than 4, or if you reach the maximum value, then we will stop the computation. And the count, right, basically is the number of the iteration you have computed. Okay, so you can imagine if you always stay, if your distance always stay within 2, then the value returned from this function will be 256, which is black. And of course, if you know over 2 in the first iteration, then your count value will be 0, which will be white. So that's how we get the colorful image we think from previous slides. Okay. Okay. So this actually will be more like what you output or you get from your homework too. Okay, we don't have this colorful image, but you're going to plot it in a great scale. Okay, so you can still see some color changes in your image. Okay, and also the amount of computation, right? Basically, the resolution of this image, right, can be controlled by your granularity of the pixel. So in your homework 2, right, as explained by your TA, there are some parameter, right, can be given to your program. One of them is to decide the area of the picture you're going to plot. Also, there are parameters to control the granularity, the resolution of the image, right? But anyway, all those parameters simply try to decide how many computation tasks or which area you're going to plot. Okay, and for every pixel you're going to plot, you have to call the function we just explained in order to determine the color, right, or the value of that pixel. Okay. Okay, so since you're going to plot the image, so you can apply a similar strategy like we show in the first example, right? You can try to partition all the tasks or all the pixels you're going to plot by row, right? And assign those tasks to your slave to do the computation. And the computation over here is a bit more complicated as we showing before, but the structure, right, the strategy you implement this parallel program is basically the same, all right? However, for this problem, especially for this problem, partition the task by row probably is not the best solution, right? Because clearly you can see that the amount of computation required on each pixel could be different, right? If this pixel color is black, that means you already iterated over 256 iterations. While if the color is white, you only do the computation for one iteration. So the amount of computation for each pixel varied widely, right? Depending on the results, okay? And also, there's no way for you to know the amount of computation for each pixel in advance because you don't know the value until you do the computation, okay? So in order to make sure the workload is evenly balanced, you actually have to apply the dynamic scheduling strategy. So you can have a more even load across all your slave processes. Okay, so that's what's interesting for your homework too. Okay, okay. So dynamic scheduling, actually you already seen it before from OpenMP, right? Remember, you can easily set by some clauses, right? When you try to use the for directive, okay? So you can choose different scheduling algorithm, including the static algorithm, scheduling algorithm, and the dynamic scheduling algorithm. Okay, but for MPI, you have to implement everything by yourself. Okay, so for homework one, you have to practice how you can implement it using MPI. Okay, but the concept is not too difficult, right? The concept is pretty simple. The strategy is because you have a master, right? So you can ask the master to keep all the tasks, right? Like all the pixel you need to compute it. And you have a bunch of slave processes, right? Waiting to do the computation. Okay? And the dynamic load balancing means that the scheduling decision is made according to the order, the task completion order of those worker processes. Whoever complete their previous assigned work or task first, he finished first, he asks the next task first. Okay, so like first come first serve, right? So the scheduling decision is, or the scheduling point event is actually driven and triggered by the slave processes in dynamic load balancing. Okay. So the idea is like showing over here, right? At the beginning, initially, of course, the master knows all the tasks, all the slaves are idle. So he can just quickly send an initial task to each of the worker first. And then after that, once the worker finish the task, he will return the result to the master and also try to grab the next task to compute. So simply just repeating this processing, right? Then you can balance the load dynamically. Okay. But the one tricky or one point you have to pay attention is how to determine when to terminate the master process and the worker processes. Okay. And the termination condition, as you can see over here, should be, of course, should be when the tasks are all get computed. So when the work pool become empty, that means you could terminate the worker and the slave processes. Okay, the worker and the master process. Okay, but however, that condition is not entirely true because don't forget, you have to weigh the result of the last tasks, right? So not only the work pool needs to be empty, you also need to make sure the result is returned to the master. Then the master can be terminated. Okay. For worker, it's simpler. The worker only needs to wait until the work pool is empty. But for the master, you also need to wait until the return results are collected. Okay. Right. Let's have a quick look at this pseudocode before we have the break. Okay, the class break. So as showing over here, okay, we have this row number indicate the task. Okay, so the number indicate which row the worker process need to compute. Okay, and for the master process, of course, as we described, in first step is just send an initial task to each of the worker processes, right? And then you have a for loop to wait for the result returned from the slaves. Okay, and whenever it receives a result, he try to send the next task to the slave, right? And the count, the row need to plus one because that means you're going to send out the next task, right? And of course, after you collect the result, you can display the results to your screen. Okay, and when you send out all the tasks, then the master will send out the termination flag or message to the slave, so the slave knows when to stop. Okay. However, as we said, for master itself, in order to correctly identify whether it can really terminate and exit this for loop, he need to check whether he already received all the return results from the slave. So that's why besides row, you will see we also need another variable called the count. So count represent the number of active processes. So as you can see over here, whenever we send out a task, count will plus one. Whenever we receive a task, count will minus one, right? So the master need to keep waiting the result from the slave, right? Until the count number is equal to 0. Okay. If the count number is larger than 0, means some of the slave is holding some task and haven't returned the result yet. So we have to call the receive function to wait for the results, right? Only when after you receive the results, there's no more task to dispatch and no more count, right? No more active process exist. Then the master can exit this while loop and terminate the whole program. Okay, so you can see the master and the slave, need to coordinate among themselves in order to correctly determine the termination condition. Okay, So this is well, an example how you could implement a dynamic scheduling strategy on yourself. Okay. For the slave, is pretty straightforward, right? Very similar to before. It simply try to receive a task, and after you receive the task, you will try to identify whether it's a termination token or it's a computation task. If it's a termination token, you will just exit the while loop and finish. But if it's a computation task with some data within, you will try to compute and call our computation function, right? And send the results back to master and try to receive the next task, okay? Until the return message is a terminate token. Okay. All right. So this is a pseudo code for your reference. You can implement your homework too based on this pseudo code, or you can just implement whatever you want as long as it's a correct way to do the dynamic scheduling. Okay. All right, so let's have a class break for 10 minutes. We will come back at 4:40, and we will introduce the second type of payroll computations.